This module is pretty much designed to show you and walk you through how you're going to construct your model, load your model, and put elevations on. Because we spent a lot of time talking about controls and calibration and getting the model running over time, but we really only got to see a teaser for ModelBuilder at the very beginning. And the reason is because when I knew that we would be spending more time on the building tools, and once we got a better understanding of how the models work. The whole point is we want to leverage data once, enter it once, and then repurpose it and re-leverage it multiple times. The model building process for the workshop, that one of the first workshops you did, you brought in the model and you built it. That took all of maybe 5 minutes to map things. You do it a second time, you'd probably be doing it in 2 or 2.5 minutes or something, even faster. If you're talking about bringing in your own hydraulic model for a municipality or an entire water system, if it's coming in from a CAD file or Excel, GIS, that process could work fairly smoothly with WaterGEMS using ModelBuilder. It could take 15 minutes, 30 minutes to map the files. Maybe you've got a dozen shape files, so you have to map those dozen shape files to a dozen different elements. Okay, so maybe it takes a little bit of time to do that. But you're only talking something like 30 minutes to go through it, check the properties. Okay, everything should be fine. However, it can quickly turn into a much more arduous journey to build your model. If you had, for example, properties or a label of your pipe that had something like E10-12-DI-1, and that was all of the intelligence for the pipe assets were in the label. Now, instead of being an individual property of the pipe, it's all in the label field or the text field for those elements. Somebody had gone through and typed in, I guess, 12-inch. This could be 12-inch diameter ductile iron. Not sure what one is. Maybe that's zone or something. Label, and all of these are it's all part of a text string. This is an example where you could have data that could end up taking you quite a few months to bring in a background layer of all of that label, then go to each pipe, double-click on the pipe, and assign properties properly. So having to do the manual assignment of diameter and class of pipe or material of pipe and everything and extract all of that from a label might actually take you a lot of time, because ModelBuilder is not going to go in and read the label and know exactly what to do, because it won't know what 12 is. It won't know what -12 is versus -12-1 or something. So when you bring it in, it needs to be a property of those elements, whatever those values are. ModelBuilder sources, again, they vary wildly. There's lots of different sources that you can bring in and build a model from. I will add, what's not on here is competitor software. You cannot bring in directly competitor software because that's just by nature. Companies don't let other companies play with their software, so we don't have a mapping tool to bring you in from another competitor software. However, you will find some commonalities, though. The commonality is EPANet, and that's primarily all of the softwares, hydraulic modeling softwares, proprietary softwares out there, export to EPANet, and then bring in EPANet model files. Now, I will caution in saying that if you're considering going this route, it's often the equivalent of feeding an elephant through a garden hose, where what you get on the other end of the garden hose is not all of the elephant, because there's lots of settings and lots of controls, and in our case, there's lots of scenarios and inheritance that don't feed and pass all the way through EPANet to, say, a competitor's software. EPANet has a lot of reduced functionality, so it can only handle in passing through whatever its own functionality is. So if you've ever used EPANet, you'd probably understand a little bit of what I mean, that you can't fit everything through that garden hose because it's a bottleneck. You lose a lot of the quality of your model. Maybe not the network itself, but there could be things like control scenarios and alternatives that are lost. The point is, in all of this the point is to use the data that's already been entered wherever it is and try and use that rather than having to pay to have the data recreated. And there's kind of two types of models. There's the hydraulic model, which is the hydraulic data calculations. You're doing all the scenarios and inheritance type stuff that we've been spending time on this week. And there's the geospatial model. This is the everything type of data. This is all of the storage data, all of the storage of assets for an organization. And it's kind of an interaction with other data sources. So these two unique models behave differently. But whenever you're running WaterGEMS inside of ArcGIS, inside of Esri, it allows you to benefit from both of these. So the tools that we're going to actually work on today in this final session are ModelBuilder, which you already got to see, and that's how we bring in our network layout and data properties. We're going to use TRex, Terrain Extractor, to bring in ground elevation. So once we have the nodes, we can bring in, drape the DEM file, Digital Elevation Model file, over our nodes, and then it will automatically pick off the elevation data points. And then after that, we can come back in with our LoadBuilder. That's the tool that we will use to load the data onto the nodes. And we could get away with doing this in ModelBuilder. However, what we're going to see with LoadBuilder, there's quite a few dials and features that we can use to in a more refined way apply those loads to our network rather than just as a single data point that came through with that node in ModelBuilder. Now, if you'd already done the work in GIS or wherever, and you're very confident in that loading data, then great, bring it in through ModelBuilder, but you can always update it with LoadBuilder at another time. This is an example of a workflow that you might follow if you are, let's say, in WaterGEMS, WaterGEMS ArcGIS. You're building a file. You would follow this path here by bringing the model data in from GIS with ModelBuilder. And then at the same time, you would possibly have your usage data, your flow meters, geocoded meters. Bring those in because they have an X and a Y format. Do some formatting, whatever you need to do to get the demands to the right values that they need to be to bring them in. Then bring them in with LoadBuilder. And once you have your model and everything loaded, you can apply the elevations. And at that point, it becomes somewhat of the same task you've been going throughout the last few days. Is you would set up initial conditions, set up any pump curves, build your controls, enter in any diurnal curves. Maybe these come from somewhere else too, but you would be putting them into the model. And at that point, you have a model that you can run. And whether or not you choose to skeletonize your model and take out some of the complexity, take out some of the laterals that you don't need, you can choose to do that to lighten the load. But this would be kind of the happy path that you would follow to get a model that you can run and calibrate and actually start doing some really cool things with. If you're building a model, you have a lot of choices, and keeping the model up to date is probably the biggest chore of them all. Once the one-to-one relationship between the model and the GIS is broken, and it will be in most cases, it becomes really difficult to automatically update the model. The extent of the divergence and between the model and the GIS, and the way that the new elements are, if there's any abandonment or how that's held in the GIS, that will determine the best way to update your model. So here's a graphic for it. Often modelers find errors in the GIS CAD maps and correct things, and then those changes need to be pushed back to the data source, or might need to be. Maybe it's calibration, maybe it's pump curves, maybe it's elevations. There's a refinement that happens because maybe you didn't have the TRex tool in your data source, but you do now in WaterGEMS and WaterCAD, so you can apply the elevations, but you still need to feed that back. And how that actually happens is with the GIS ID. So there's you can hold one or more GIS ID tags per element, and that's what's going to allow all of this kind of coordination in concert, all of these changes to be able to be kept up with. Now we're going to actually start going into, I'm going to show you some of the tools here. ModelBuilder itself, here's a kind of a breakdown. WaterCAD, ModelBuilder inside WaterCAD can bring in old WaterCAD files, EPA.NET files, Bentley Water files, CAD files. It can bring in Excel files and quite a few others. If you are trying to synchronize, then you would just be synchronizing with the drawing file or the shape file or something. ModelBuilder maintains a synchronization That way you can synchronize the source and the destination, and those are some of the questions that I asked you to kind of read through with ModelBuilder before, and we're going to get into a little bit more detail on those. If you're using WaterGEMS, that's where you can actually touch and manipulate the geodatabase itself and synchronize with the geodatabase, and that may be advantageous for you in that place to have WaterGEMS, because then you're not having to export a geodatabase to a shapefile, go make some changes, and then have an additional file that you need to route things back through to get it back into the geodatabase. It kind of cuts out the middleman, in that case, the shapefile, by running WaterGEMS inside of ArcGIS. The city has a GIS, and if you want to run the model, you don't want to be storing all of the results of the model in the enterprise-wide GIS. You have to have your own kind of GIS to store the model data, and that might work out. Bigger cities are a bit more strict about this. The citywide GIS is not the best place to store like the what-ifs. So this might be an opportunity for you to think about and consider how these model data sources are going to flow and update. Because if you do some cleanup and do some changes and some calibration in the hydraulic model, how are you going to feed that back to where it can be repurposed, or is the model then going to become the de facto data source? There's a philosophy that no one city, there's not one way for every city. It's going to be dependent on every municipality, every organization, how the data flows and how the departments are structured. But the overarching rule of thumb is enter the data once. I have seen in some cases some fairly large cities that end up actually updating data in 5 different departments. So plans were copied and sent out if there was any type of changes. 5 different departments were having to keep up with that information. Now that's not ideal, because that means 5 different departments are having to do the same task of updating a model when it could have been done once and shared. So those kind of decisions do end up costing a lot of time and money to keep multiple sources up to date. Now, speaking about keeping files up to date, one problem we solved with the latest release, or with I think one of the later Select series and now obviously Connect, is maintaining coordination between the model and the GIS source from which it was created. The model's initially in sync, so on day 1 everything's in sync. You extracted the data from GIS, everything's okay. But over time, both the model and the GIS are edited. There's changes that are made. You're calibrating over the model. The GIS department is adding things or changing things. There's a different cycle or rate at which they change things to. With other software, updating the model from the GIS is extremely painful, but with V8i and one of the Select series in V8i forward, we took a lot of the pain out of the modifications by allowing that synchronization to happen and rectify all of those changes. And again, that's happening because there's that GIS ID. If you, at some point, lost the GIS ID, then you're not going to be able to remap the elements back together. The GIS data is going to have everything in the kitchen sink. It's a much different view of the world than the hydraulic model. Sure, there's points and lines and junctions and everything in both, but we might need a way to convert all of the point feature data to model elements. And in this case, we can use Scalabrator to kind of reduce some of the complexity. And in this case, reducers would actually be a junction. New pipe would actually just be another pipe. Laterals would be a junction. So we can, with ModelBuilder, when we bring in the data to build a model, we're going to end up with junctions and pipes. But then it's a matter of how you want to maintain and preserve all of those pipes. Do you want to run Scalabrator and reduce the complexity to where you have reduced all of the pipes in series down to just 2 in this case? You can do that, but again, by manipulating the model with Scalabrator, the ID that used to be for this element here is now no more. The ID for this element, this one, let's see, a few elements. There's quite a few IDs. There were ID tags, but now they are no more because we have a new equivalent pipe here that was created in Scalabrator. So if you are trying to preserve the one-to-one relationship and ever map data back, then this is one of those decisions that you would need to kind of make with Scalabrator and make that decision wisely. We've already gotten into some of the mapping, and I'll just have you refer back to this slide if you need to, but there's a few slides in here that show you how different elements map to different WaterCAD WaterGEMS elements. Air release valves map to air release valves, T's map to junctions, pumps to pumps, and then there's a few tables here. Hydrant and laterals, there's one. Hydrant and laterals can actually be brought in as a hydrant, just as a hydrant. Customer laterals themselves, you can bring in the customer laterals, or you can have a customer meter element. So that's the little house factory looking symbol. So those are a few that might be slightly different. When you do run ModelBuilder, you have the ability to clean up some of the data though. Now that's pretty important because there may be lines that weren't snapped to endpoints, there were endpoints, or maybe there were no endpoints. So you can rectify some of the errors in the data with ModelBuilder. You can fix some of the connectivity issues. Maybe there are two nodes that should be connected but were not. There's pipes that appear to be connected but they're not, even though there's a node that's drawn that those pipes aren't snapped to. So sometimes this can happen that the requirements of the CAD files weren't followed through all the way through. Maybe pipes were crossing and there should be junctions. So you can have quite a few of these come up or creep up in a model that ModelBuilder can then in turn help fix. So to resolve this, it can add in nodes, it can snap pipes together, it can snap the pipes together by a tolerance. So you would give it the tolerance something reasonable, half a foot, half a meter or something. If you did a tolerance of 5 meters, then what it's going to do is snap together pipes that are within 5 meters of each other. Now, that may be okay if you have a really spread out system, but if you have some tight networks near a pump station, that might kind of get a little bit weird on you. So set the tolerance accordingly for however you want your system to snap together and clean up. Set it as a really small tolerance, I would suggest at first. Some considerations: you don't have to bring everything in with ModelBuilder. You don't have to connect to everything, but things like installation date, I, for one, would like to bring in an installation date from GIS data. I might want to use that because it's something I could then filter on and better help me assign C values or better help me assign materials or something. So there's some data properties of a pipe or a junction that you just might like. Number of breaks, there's another good example of one that you would like to bring in. Elevations, you don't need to worry about those too much. If you have them, great, bring them in with ModelBuilder, but otherwise TRex can take care of it for you, as you're going to see in the workshop. And then same thing with demands. You can bring them in with ModelBuilder, but LoadBuilder gives you a lot more flexibility. Bit on file types. So the SQLite file, if you had to and you were running out of time, it was a top secret mission, you had to go in and there was one file you had to grab, the SQLite file or the MDB file is the one that you would need to grab. That's the important one. If you're backing up anything and you accidentally deleted files, don't delete the SQLite or the MDB file. The MDB file extension would come if you have a V8i prior to Select Series 4. Moving forward, we transitioned it to a SQLite storage file because it's lighter, it's faster, it speeds the computation processing that's going on in the background. So SQLite or MDB file, Access Database file. The other files are dependent on the platform that you're coming from. Today, you're in standalone, so there's going to be a .dwh file. If you're in ArcGIS, there's going to be an MDB file, maybe some other file types there. And then the .wtg file, that's just presentation data, color coding. It's no big sweat. If you lose it, you just recreate a few things. It's not like you're losing scenarios and inheritance or anything. That's all part of the SQLite file. Another screen to refer to for file types and what they all mean, if ever you need to. Okay, here's that pretty DM file that we saw earlier that's actually coming from ArcGIS. You can bring in elevation data, whether it's from GPS data, DEMs, In some cases, there may be more accurate information in some regions of the city or in some regions of the water system, so you can create a selection set and only update that donut or that portion of the water system. Rather than updating the whole thing, you can choose to only update a certain set where you got new data or wherever you actually care to update it. The digital elevation model files, it could be a raster or a tin, and rasters are really big files, tins are really small, just in how they actually store the data. And whatever format it is that you're bringing the digital elevation model data in as, of course you want your distribution system to overlay on top. You want the DEM to fit wherever that water system is. If it doesn't, then the suggestion there is to mosaic or seam your DEMs together. That way you only have to do this once. You can do it again repeatedly as you draw in new piping, and then just rerun through TRex. Running TRex, mosaic any rasters or your DEMs together. And standalone, you can do this in standalone MicroStation. It's available in all of them. Know your spatial reference, because your digital elevation model has to have the spatial reference that's relative to the model. If you just start drawing the model in standalone, irregardless of spatial reference, your DEM is going to be coming in somewhere, but probably not where your model is. So you need to make sure that when you do start creating your model, you're building it in the right orientation that it should be. Now, again, when you run ModelBuilder, it's coming in with the X and Y coordinates. So those should be the correct spatial coordinates for all of those elements whenever ModelBuilder brings it in. Check your units in TRex, select your data source, it's DXF, Len XML, Esri shapefile, whatever the format is. Create a new physical alternative, or you can overwrite the physical alternative, and it'll give you a preview. So here's the screenshot that comes from TRex. You select your data source, the field that you're picking the elevation data from in the file, set the units, and then this is where you can apply it to just a selection set, just a few set of nodes, or all of the nodes altogether. And then it gives you a preview just to make sure that, hey, Mr. Muller, Miss Muller, this is what you're about to do. Is this okay? You could be bringing data in from individual customer meters. In this case, this is a screen where we have meter data based on each customer that have been resolved to an X and a Y coordinate. This doesn't mean that the model is picking up 1525 Akron Street. If that was your address, your own address where you live, that was really creepy. But if not, 1525 Akron Street doesn't have an X and Y coordinate unless you have somehow distilled that X and Y coordinate down, or that address down to an X and Y coordinate. Then you can actually do something with it. You could just be bringing in meter route flows into pressure zones, and that's fine. We would just have a polygon to represent that, the downstream of that flow meter, where whatever nodes were representative of that flow meter. It's not as precise. Pressure zone flows, they are not as precise as having individual customer meter records, though. Or moving in the other direction to less precise, we could have polygons that represent densities. So the polygon has we know 300 people are in that polygon, and we know there's 200 gallons per day or 100 gallons per day per capita, or maybe even it's acres in land use. So there's different methodologies you can use to load the model, and we'll go in the workshop. We'll actually go through different methods to use. So there's the point data, that is the customer meter data that will ultimately be loaded to a node. Granted, in the model, we have these customer meter elements, so we can preserve the data on a customer meter element, but it's got to get into the model somewhere. And we'll see that passing through into the node. Or we can load it by polygons. This would be from, say, meter routes or pressure zones, where a particular pressure zone had a particular flow that went into it, and we have a set of nodes within those polygons. I'll show you how that's going to operate behind the scenes with LoadBuilder. Or, as I mentioned, the land use. If we have land use and density based on some loading table based on the type of land use that we have. We can then apply loads to the model, loads to the nodes. The customer meter data is probably the most accurate and highest resolution data. The downside is it's not including the unaccounted for water. So we spent a little bit of time in one of the other lectures talking about unaccounted for water. But if you have flow meter data for individual residences, it's not including that. So if you do have a substantial known unaccounted for water, you would need to come back and add that into some of the nodes. Or if there's areas where you know it's more prone to leaking, you might add more water loss to those nodes as well as additional demand collections, or as additional demands. System metering data, that top-down method, you're going to be loading by Polygon at that point. It's very coarse data, but it also accounts for the unaccounted for water. So the different method you choose, one may be more accurate or inaccurate, but again, you can treat all of these as different demand alternatives and run your model against calibrated data and begin to see if one is more accurate or less accurate. Now I'd like to introduce the customer meter elements to you. If you're on one of the earlier versions of the 8i, you wouldn't see this. With the Connect version, you do see it, and it is to represent or preserve the location of the individual meters. It'll preserve the X and Y coordinates. You can do some querying. You bring these in with ModelBuilder, but you can do some querying and how they associate their loads to the nearest pipe or the nearest node and things like that. We can load our model accurately from those. Maybe there's some flex table data that you might harvest from it as well. Your flow meter data that comes in, usually it isn't in a form you want, so you've got some flow rate, but over a certain number of days or volume of flow. What you really want at the end is a gallons per day, liters per second. You want some cumulative usage. And then you're going to come back and apply a pattern on the demands. So you'd have to go, and convert the data from the water system data, from the customer billing data over to something you can use. Get the X and Y coordinates. There's some address matching services. Tiger's an example of one. And once you have the X and Y coordinates and the flow rate, and you have some appropriate demand patterns or demand curves to use, now you can actually be rocking along with LoadBuilder and load everything into LoadBuilder onto your model, apply the patterns, and you're heading on down the way to a good calibrated model. The amount of water that's produced is equal to the amount of water that's billed plus everything else that was lost. If we assume that the unaccounted for water is some percentage of production, we'll call that U here, then we can play around with some numbers and represent the amount produced relative to the amount billed divided by 1 minus this percentage. Now, again, we're kind of monkeying around. We're coming up with numbers here, but trying to reduce it down to relative to how much unaccounted for water there is. You have to know what the billed water is by node and system-wide, what that unaccounted for water is. What I would say there is you're actually looking at how much went out the treatment plant versus how much was billed, and then that gives you a percentage. Okay, there are 3 ways that LoadBuilder will point the meter data into the model. The first one is the nearest node, to where based on the meter data it will load to the nearest node, load to the nearest pipe, or load based on some polygons where you're driving it and telling the model use these polygons to load to these various nodes. Now the third case is going to take more time simply because you're having to draw the polygons. In other cases you may know the meter data in a small area like a meter route or something, or a meter section of a system. Let's see, to use this data you'll need to know the flow and the polygon for which the flow is consumed or consumed by. So in this case, this is an example of a polygon with nodes within it, and there would be links and everything connecting those nodes, but I just want you to focus on the nodes. That there is some flow that went into this polygon, so now with equal flow distribution method in LoadBuilder, it's going to take the 100 gallon a minute, divide it by 5 because there's 5 nodes, and say, okay, every node gets 20 gallons a minute. Proportional to the size of each node is slightly different, which is another method. Then you have nodes that are proportionally being attributed more size. They would get the greater share of that 100 gallons a minute of load. Proportional by some population. There's Polygon data in here too that will help drive whatever the greatest demand would go to these nodes. Now, you can kind of see at this point we're starting to take some wild guesses on how much load should go on each node, and this is probably again another good reason why, if you're looking at comparing pressure data down to the decimal place, if you've loaded your network using methods such as this, where it's proportional to area, proportional to some criteria, and how you're distributing loads on all the nodes, you're probably not going to have the ability as precise as you would like to compare for calibrated data. Whereas if you're loading from actual meter data, coming in geospatial locations for your meters, you're going to be much more precise and be able to compare the node values that you get, the pressure values, to the actual real-world values, pressure data in the model compared to the pressure data in the real world. We've been talking about node service areas, the area served by a node, but how do you create these? In the old days, you drew them by hand, and some of our users did this. But there's also an automated method to do this called the Polygon generator, which uses the Thiessen Polygon algorithm. The only thing you have to do is be careful about the outer edges of the Thiessen Polygon generator. And how it works, this is again part of LoadBuilder. It would create the polygons for you. You would have the nodes, then it would go in and draw lines between the nodes connecting each other. Then it would do some bisecting of lines to generate the actual polygons. It would kind of delete those initial lines away to where you end up with polygons that are representative of area. So this is kind of an automatic step that you can run through with LoadBuilder to accompany LoadBuilder. The downside is you still have to include the outer surface as a polygon. That way there's some limit. Otherwise the polygons for the outer nodes could end up being quite large. If you have your demands assigned to nodes in GIS, you can import them with ModelBuilder. But unfortunately, most demands are in some sort of format, some of their computer or whatever, and the meter records are not kept by node unless the billing system and the GIS are set up for this. So import the demand data when it's in the format that you're able to bring it in this X and Y coordinate system. And then with LoadBuilder, what we want to do is we want to come up with a generalized demand builder, but knowing that every system is different and how you come up with your demand data. So what we ended up doing is coming up with about 8 different methods that are going to be used to cover most of the ranges that you can bring in your meter data. So in LoadBuilder, we have the ability to treat the data in 3 different sections, or sets, if you will. Point data is the most precise. This is our meter data, and we can load them by the actual billing meter. This would be the happy path, the best scenario for you to be in to load your data properly, and load just by billing meter aggregation. You can load also to nearest pipe or nearest node. Those are some other options, but you're still bringing in point data. Then there's also area load data and population land use data that we're going to use in the LoadBuilder if we have time. We'll get into those. That we can actually bring in based on polygons. Now, that data is less precise than the point load data. We'll go to Tools, LoadBuilder, select the method that we're going to use, select the source we're going to connect to, apply any multipliers because LoadBuilder will allow us to do that. We can right there apply any peaking factors, preview our data, and then apply, and again we can still create a selection set. So here's an example of the multipliers. We can adjust things, we can apply patterns, we can do all of this in LoadBuilder, and then it would apply to the nodes. And just to keep us from overriding, say, our base demand data, we can set a new alternative create a new alternative here. That way it doesn't override anything we don't want it to override. And this would be a child. You can pick the parent here, so you can set up the associated child-parent relationship right here in LoadBuilder.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.